The Thevenin's equivalent circuit is not the only possibility to simplify a generic two-terminal component made by resistors, short circuit, open circuits, voltage generators, and current generators. In fact, we can repeat the previous study, but this time, instead of using an external current generator, we can put here a voltage generator whose electromotive force is V, and calculate the current I that is supplied by the two-terminal component, and then applying superposition we can try to find out a relation between the voltage and the current. Again, applying superposition we can say that the current I can be obtained as the sum of the contributions of the voltage generators. So for K from 1 to the number of voltage generators of a coefficient delta K EK plus the sum of the contributions of the current generators. So the sum for J from 1 to the number of current generators of epsilon J A J plus the contribution of the external voltage generator. We can call this contribution eta V. Again, the first two terms represent the contribution of the inner generators, while the last term is the contribution of the external generator. We can consider independently the two contributions. The first one represents the current flowing through the external generator when it is off, so when it's replaced by a short circuit. For this reason, the current is called I0, and it is the short circuit current with short-circuited AB terminals. The second contribution is the contribution of the external generator when the internal generators are off. So replacing the voltage generators with short circuits and the current generators with open circuits, we can get the current I double prime as eta V, that is, eta is 1 over the resistance of the passive two-terminal component at the terminals A and B. And since this is studied according to the active sign convention, we also have to add the minus sign. So this equation is nothing but Ohm's law applied to the passive AB two-terminal component. To summarize, the current I0, also called IN, after the Norton's equivalent, is the short circuit current measured or calculated when the terminals AB are short-circuited, whereas the resistance RAB, also called Rn, is the equivalent resistance measured or calculated when all internal generators are switched off. The final equation is then the current I equals the short circuit current minus the voltage V divided by RAB. And this equation can be represented by a simple two-terminal component made by a current generator in parallel with a resistor. We can represent this equation in the VI plane. When the voltage is 0, the current equals the short circuit current, I0, and when the current is 0, the voltage equals RAB I. The equation is the equation of a straight line passing through these 2 points. This characteristic is the characteristic of current generator, whose current is not fixed, but the larger the voltage, the larger the reduction in the current. An interesting analysis is the possibility to pass from the Thevenin's equivalent circuit to the Norton's equivalent one. To do so, the first thing that we can try to do is to get the Norton's parameters from the Thevenin's equivalent. What we have to do is simply to calculate the parameters by short-circuiting the AB terminals and calculating the current that is flowing through the short circuit. And this is the current IN. In this case, IN is simple because it is nothing but the current supplied by the voltage generator. So it is VTH over RTH. Then, without redrawing the circuit, if we switch off the voltage generator, the resistance that is seen at the AB terminals is exactly RTH. So, if we want to pass from the Thevenin's equivalent circuit into the Norton's equivalent circuit, we have to take a resistance that equals the resistance of the Thevenin's equivalent, and the short circuit current is equal to the open circuit voltage divided by the resistance. Similarly, if we want to transform the Norton's equivalent into its Thevenin's representation, what we have to do is to calculate the open circuit voltage. The open circuit voltage is, in this case, the voltage applied to the resistor Rn. So, since the terminals are open, what we have to do is to calculate Ohm's law, where the resistance is Rn, and the current flowing through this resistance is exactly the current of Norton's generator. So we have that VTH is Rn IN. And similarly to what we said before, if we switch off the current generator, so we substitute the current generator with an open circuit, the resistance at the AB terminals is exactly Rn. So RTH equals Rn. So, if the value of the resistance is not 0 or not infinity, it is always possible to transform a Norton's equivalent into the Thevenin's equivalent and vice versa. There are just a few components that doesn't have the Norton's representation or the Thevenin's representation. For example, if you consider a simple voltage generator, it has in the Thevenin's representation, because if you consider a resistance in series with a generator that is 0, you have exactly the generate case of the Thevenin's equivalent. But this element, the voltage generator, doesn't have a Norton's representation. On the other side, a current generator has a Norton's representation by using a resistance that goes to infinity, but it doesn't have a Thevenin's representation. Now let's see how to apply the Norton's equivalent to solve an exercise. In this example, what we have to do is to substitute the part of the circuit highlighted in red with its Norton's equivalent representation. This is the exercise that we solved before, and so we know that the equivalent resistance at the AB terminals, when we switch off the generators, is exactly the resistance that we have already calculated for the Thevenin's two-terminal component, and so it's R2 in parallel with R4. Regarding the short circuit current, what we have to do is to short circuit the terminals A and B. So we have to get rid of the resistor R3 and substitute it with a short circuit and calculate the current through the short circuit. We have here two generators, so we can apply again the superposition principle, and so we have to calculate IN as the sum of two contributions. The first contribution is calculated when E1 is kept on and E5 is switched off. In this case, the resistance R4 is short-circuited by the short circuit between nodes A and B, and so IN prime equals E1 divided by R2. If we switch off E1 and we keep on E5, we have a similar circuit to the previous one, where this time R2 is short-circuited, and so the second contribution to the current IN is E5 over R4. If we sum up the two contributions, IN equals IN prime plus IN double prime, or E1 over R2 plus E5 over R4. Once we have calculated the two parameters that define the Norton's equivalent circuit, we can connect again the resistor R3 to the terminals A and B, and so we can solve with respect to the current I3 this simple circuit. In this case, it's easy to calculate I3 applying the current divider rule. So the total current divided is IN. At the denominator we have the sum of the two resistors connected in parallel, Rn plus R3, and at the numerator we have the value of the resistance where we are not calculating the current, so Rn. Up to now, if we have a circuit with more than one generator, what we have to do is to apply superposition. We don't have any other method to solve quickly the circuit. What I'm introducing now is a new formula that allows us to study circuits with more than one generator, but these circuits are not as general as those that can be studied applied superposition, but are specific circuits with a specific topology. The topology is the parallel connection of two terminal components that are represented as their Norton's equivalent, or at least can be represented by a Norton's equivalent circuit. Let's consider, for example, the circuit in the figure. Here we have two branches that are represented by a Thevenin's equivalent circuit, but we can think that any Thevenin's equivalent circuit can be also represented as its Norton's equivalent. Then we have a resistor, and then we have current generators. Now, what we can do with Millman's formula is to calculate in a single step the voltage that is applied to these components that are connected in parallel. So the voltage that we have between the nodes A on top and node B at the bottom part of this circuit. Let's call this voltage VAB. In order to prove how the formula of Millman's is represented, we have to apply a two-step procedure. In the first step, we assume the voltage VAB as known, and we calculate the currents in each branch. For the currents, we assume the same convention, and this convention is that they are all going inside the node A, where the node A is all the part of the circuit that share the top potential. If we want to calculate the current I1, we can apply Kirchhoff voltage law at the first branch, where the closure of the path is made by the voltage VAB. So, considering that the voltage drop across the resistance R1 is R1 I1, we can write that E1 minus R1 I1 minus VAB is 0. So we can calculate the current I1 as E1 minus VAB divided by R1. In a similar way, we can calculate the current I2 by applying Kirchhoff voltage law to the branch 2 and using VAB as a closure for the closed path. We have minus E2 minus R2 I2 minus VAB equals 0. So we have that I2 equals minus E2 minus VAB divided by R2. For the third branch made by the resistance R3 only, we have that the voltage VAB is applied directly to that resistance. The resistance is studied according to the active sign convention, and so we can write Ohm's law in the form VAB equals minus R3 I3. So I3 equals minus VAB over R3. For the branches with the current generators, the current is impressed and equal to the current of the current generator. In the case of the current generators A1, we have that I4 equals A1. But for the current generator A2, what we have is that the impressed current has an opposite direction with respect to I5, and so we have to say that I5 equals minus A2. The second step is to apply the Kirchhoff current law to node A. Since all currents have the same direction, we can write that I1 plus I2 plus I3 plus I4 plus I5 is 0. And so if we use the results of the previous step, we have E1 minus VAB divided by R1 plus minus E2 minus VAB divided by R2 plus minus VAB divided by R3 plus A1 plus minus A2 equals 0. In this formula, the only unknown is the voltage VAB, so we can factor out with respect to VAB. If we move the terms with VAB at the right hand side, we have E1 over R1 minus E2 over R2 plus A1 minus A2 equals VAB that multiplies 1 over R1 plus 1 over R2 plus 1 over R3. And so, if we write with respect to VAB, we have a formula where the denominator is made by 1 over R1 plus 1 over R2 plus 1 over R3. And the numerator is made by E1 over R1 minus E2 over R2 plus A1 minus A2. This formula is known as the Millman's theorem. If we want to comment out this formula and try to get some rules to memorize and remember this formula, look at the denominator. We have the sum of 1 over the resistance that we have in each branch. In this case, we have 3 resistances in the first 3 branches, and so we have 1 over R1 plus 1 over R2 plus 1 over R3. Now, let's have a look at the numerator. At the numerator, we have all terms that have a current as dimension. The values for the branches where we have the voltage generator in series with a resistor, we have a term that is the voltage of the voltage generator divided by that resistor. And for the current generators, we have the current impressed by these generators. For the signs, look at the direction of the voltage of the voltage generators. If we have the polarity of the generator that is pointing up, so the plus of the voltage generator is pointing with the same direction of the voltage VAB, we have a plus sign, like here. Instead, if the plus of the generator is pointing down while the tip of the arrow of the voltage VAB is pointing up, we have a minus sign. For the current, if the current is pointing up, like the voltage VAB, we have a plus sign. If it is pointing down, we have a minus sign. Now, let's try to solve the circuit that we have solved in many ways up to now. This circuit can be directly solved using Millman's formula because we have 3 branches. 2 of them are made by a voltage generator in series with a resistor, and the third one is made by a resistor only. So it's pretty easy to use Millman's formula to calculate this voltage, V3. In this case, V3 is equal to fraction line. The denominator is made by 1 over the resistances that are in each branch. So we have 1 over R2 plus 1 over R3 plus 1 over R4. At the numerator, we have 1 term for each generator. Here we have 2 voltage generators, and so we have terms of the form E over R. So for the first generator, we have E1 over R2, and for the second generator, we have E5 over R4. Both terms have the plus sign, since the direction of the electromotive force of the generators are in accordance with the voltage V3. Once we have V3, it's simple to calculate the unknown I3 using Ohm's law. So V3 over R3. So for this specific circuit, the Millman's theorem is the simplest way to get the result.